Mr. Klupar was Director of Engineering at NASA's Ames Research Center. Thank you.
Thank you very much. Can you hear me okay? Yeah. Thank you very much for spending part of your Veterans Day with us here in this cold, I guess it's a warm day on Mars, but it's a cold day here. So I work for Breakthrough, and I just want to give a little background of what the Breakthrough Foundation is, and then talk about Starshot, the interstellar project that we have. So Breakthrough Foundation is a foundation that's supported by a bunch of billionaires out of Silicon Valley, and it has two divisions. One division is the prize division, where they give out $3 million prizes, 7 to 10 $3 million prizes. They just did it November the 4th. They give it in biology, math, physics. It's trying to make science cool, which we need more of. And then the other part of the other division in Breakthrough is called the Breakthrough Initiatives, Life in the Universe initiatives. And our mission is to search for life in the universe. And we have 5 different initiatives to pursue that, and we're spending somewhere on the order of $30 million a year doing that research. And the 5 initiatives are Watch, Listen. Listen is a SETI one. Watch is astronomy. Then there's Starshot, of course, and Message, and I'm forgetting the last one. But the Starshot, this picture is supposed to wonder where did life come from? Was life seated in the Earth? This is not a target on Wichita to make it warmer. It's really asking the question of how did life start? Because there's really no evidence on the Earth of how life started. A lot of people think it started from other places, but I digress. So we have the Starshot initiative, which is we've set up a committee for that initiative, and it has there are a few committee members in the audience, and the committee is chaired by Avi Loeb out of Harvard. And we also put a little picture there of the interstellar asteroid, which Avi is really excited about. And he thinks that it actually might be a light sail. And he's done some calculations and published some thoughts in the archives that suggest that maybe it could be a light sail. I wouldn't say maybe it is. It's not ruled out, I guess, is the best way to really say it. Because there's really very little evidence, just a couple of images. Okay, so Starshot, a little bit of background. In 2016, we started to look at the different ways to do interstellar travel, and we had some help from Kevin Parkin over there. Is our system engineer, and he did a bunch of calculations, and we came up with really the only solution was to do a light sail, a laser sail. And this is a graphic that kind of describes what the light sail or what the mission is. So in orbit at about 60,000 kilometers, there's a mothership, and it deploys a light sail, a laser sail, which weighs about a gram and is about on the order of 4 meters across. And then lasers on the ground illuminate it, put about somewhere between 50 and 100 gigawatts of power on it, and it gets it moving to 20% the speed of light. So it's quite audacious, quite ambitious, but it's the only real way we think that it can actually work. The point of this slide is that we didn't start from zero. There was a lot of people that have been researching this for a very long time. There's been a lot of people that have worked on this for many years, and some of them in the room here now, although I don't see Jeff, but, oh, there he is. So, you know, it was well, the first person I saw was Robert Forward doing a lot of work in the 70s, published a lot of work, then JPL, and then Jeff did the work, and the most recent work was Phil Lubin, who I guess is going to be here later in the week. Wednesday? Yeah, Wednesday. So you should ask those guys all the hard questions. Only ask me the easy ones. But it's really enabled by the fact that lasers are getting better, and that electronics are getting smaller, and that the metamaterials that we're building are getting better. So the Starshot objectives are to basically go visit an Earth-like planet within 5 parsecs of the Earth. That's about 15 light years, and to take pictures and send them back, and to do this all within 30 years. These are the goals that the funders have given us, and we've laid out a program to try and do that. We've divided, you know, with an ambitious project like this, you'd like to work on everything all at once, but you really can't. So we decided that there were 3 things that we wanted to work on: the Photon engine, the Sailcraft itself, and the communications. So this is what we're devoting our energies to right now, and we'll talk about the Photon engine first, which is chaired by Bob Fugate and Wes Green. We've designed it to have 3 phases over the next 10 years. We're right now in the phase 1 concepts, trying to understand concepts and analysis, and then in the second phase we'll start building lab hardware, and then the third phase we'll do on-sky demos. Now, the thing that really surprised me the most about the efforts was, I thought we were going to design this system and we were going to figure out what this system was through our efforts, but really what we found out was we're figuring out what it's not. We're discovering how to build this thing by figuring out what we can't build. And you might think, well, you're going to build a gigantic mirror on the ground, and but it's got to be, you know, on the order of several kilometers across, and you have to have a secondary mirror up there at 3 kilometers. So that's it certainly can't be that. Then we thought about, well, maybe you could put a bunch of lasers and you know, comfortably space them off across this large several kilometer area. Turns out that doesn't work either. It's got to be a lot more densely packed than that. Then we had some artists do some pictures, and they designed the lasers to be more RF, if you will, but that's not going to work. We've really, right now, I think, I don't know if Kevin believes it, or I don't know if anybody else in this room believes it, but I really think that we're going to end up with densely packed 20 centimeter, 10 to 20 centimeter wide mirrors on very restrictive mounts, probably silicon carbide, but there's going to be an infinite number of them. It's going to look something like this. So the price of all these moving parts and building this is really going to be the driver. So maybe it won't actually look like that. Maybe it'll be more compact V-cell kind of arrangement that looks like this, again, densely packed across the whole area. So right now in the phase 1 in the Photon engine, we have 12 different, 12, oh, that's interesting. I just noticed that this starts with 0. We must have had a software designer make the chart. So we have 12 different contracts in place now, and this is the list of the organization and the location, and they're mostly universities, and they're basically studying the basic analysis to how to coherently combine an infinite number of lasers at a price that's less than the cost to build the Large Hadron Collider. So $10 billion-ish. I mean, you could do this today if you could spend a few trillion, but we don't think that's reasonable. Okay, then, so that was the Photon engine. Then the second committee that was stood up is called the Sailcraft, and that's led by Harry Atwater down at Caltech. And we've set up, again, another 10-year plan in 3 phases, basically. And so for the next 2 years, we're going to work on building the material, figuring out which materials to use. Right now, my favorite is silicon or gallium arsenide, something like that. So a semiconductor, which is kind of surprising, but and then come up with the construction methods, and then start to build in-lab demonstrations, and then so at this point, the materials they're building are specks of dust. They're very, very small. We hope by the end of 2 years to build something that you could actually see. And actually, I think that was the original plan. I think we're going to actually do that faster than we're predicting. Oh, here's the materials we were talking about. That, again, this is my favorites down in here, but there's also diamond and just straight amorphous silicon, and those are the materials that we would choose for the sail. But the sail, it's not like building a carpet or a rug. It's really more about the method that you build the sail itself, and about how you put together the atoms. We're thinking it's going to be about 400 atoms thick, and the way those atoms are assembled allows for the reflection of the light off of the material. Not a material property per se, but more the way they construct it. So that really drives us to an ultra low absorption. That's really the most important attribute for the material itself. And again, you can see this. I like this picture here in the middle. These sort of describe to me the way it works. If you space these holes or pillars at the right distance apart, then the photons actually interfere with the materials, and then they reflect off. And there's the equation we'll have the test on later. The other problem it's not just a materials problem, it's also a stability problem. How do you ride the beam? So if you're going to put 50 to 100 gigawatts of power onto a sail, how do you keep, it's like that beach ball at the exploratorium riding on the column of air. How do you keep something riding on such a powerful beam? So there's studies on that, and we've had several different approaches, and here's some simulations that show bad things happening to the sail, and you have to have incredible control over the beam quality, and the optics, the entire system, and the sail and the material itself. let's see if we can get this this guy to run. Oh, there it goes. So this is just a simulation that was done that shows a spinning sail, and I really believe that you're going to have to spin the sail, and the problem, of course, is if you spin it too slow, the sail will collapse. So that's kind of a problem. And but on the other hand, let's try this one. If you spin it too fast, then the sail disintegrates also. So I guess we need the Goldilocks sail. Or on the other hand, here, let's try this one. If there's a wrinkle in the sail, if the sail isn't perfectly controlled, the performance of it is perfectly controlled, it will also, this is just with a small wrinkle in it that we couldn't even see. And by the way, this, of course, is, I'm not sure. This all happens in less than a second. So riding the beam is a really important and really significant activity that needs to be done that is difficult. So we have 10. We have 10. Oh, these started with 0 again. So we have 11. We have 11 contracts distributed mostly to universities that are studying these problems. A few of them are studying the sail stability, but most of them are materials. Yeah, you see stability, but the rest are materials. Now the new subcommittee that we just started is called Dave Communications. And the chair he's just installed this month is Phil Moskoff out of ASU, professor at ASU. And the question is, these are, I'm sorry I missed Dave's talk, but I had my tongue stuck to a light pole outside. It was so cold. But I'm sure he's gone through many of these problems. Actually, we've had long discussions on most of those. And this is not meant to be a complete list. This is just meant to be the favorite ones and the most recent ones. So we've divided the problem into 3 areas. The onboard transmitter, the receiving station, and the protocols and mitigation approaches. And so those are the areas that we're looking to invest in over the next 10 years, and to have demonstrations. We are talking about having a industry day. I don't know if you call it industry day, university day, study day, a workshop in Tempe, maybe March, April, hopefully before it gets too warm. March might be too late, but sometime in the spring. So stay tuned, and we'll talk more about it. So it's going to be again, a competitive approach with a phase 1, phase 2, phase 3, and we expect to make the phase 1 awards sometime next year. Okay, there's another thing that's also kind of exciting that we're talking about that we're going to do at the workshop too, also, and that is we're talking about doing some kind of near-term demo mission. And this is still very, very preliminary. We're not actually sure what that mission should look like, but we're pretty sure we want to do a near-term demo mission. So I'd like to solicit ideas. What we're thinking is taking some of the materials that we have and testing them in space with a very small laser, maybe a 20-watt laser, maybe some of this sail material that we have out there. And also to integrate the chipsets. I think a couple of years ago we showed you guys those chipsets. Some kind of spacecraft. What is the spacecraft part of the sail going to be, the Sailcraft? So come and find me if you have some great ideas about how and what to do. I'm sure I'll regret that, but no, you are the guys who have been thinking about this stuff for the last forever. So please, I don't know when this demo will be, but I would hope it near term is kind of a hint. Sometime soon. What we're worried about is that we're doing all this research at the universities, and it's sort of, that entertains and excites some people, but the rest of the broader community sees nothing. They don't read the papers those guys publish. So that's sort of, that's the idea behind this mission. So I think that's the last slide, and